everyone, I am Akhilesh Kumar Srivastav from ABS Engineering College, Ghaziabad. In the series of the operating system lectures, today we will discuss about the prediction of the burst time in the shortest job first algorithm. We have seen that whenever we have to execute the shortest job first or the SRTF algorithm, that is shortest remaining time first algorithm, we should have the information about the burst time of the processes in advance, but practically it is not possible to have this information. So, we do some kind of the computation to find out this figure. So, the outline of the today's lecture would be, we will first discuss about the scheduling criterias, then we will discuss about the prediction of the burst time with the static approach, and then we will discuss about the prediction of the burst time with the dynamic approach, and we will then solve a numerical finally. So, I already have told you that the SJF or the SRTF algorithm is completely dependent on pre-known burst time. In case we do not have the burst time in advance, these algorithms are of no use. So, we must have some mechanisms by which we can predict the burst time. So, the prediction of burst time is an arithmetic process. We need to perform some computations based on the previously executed processes. The execution of the previously executed processes and their burst times are stored somewhere for the computation of the burst times in the future. Now, let us first have a look at the SJF and then the SRTF algorithm. We will quickly go through these two techniques, and then we shall see that how the prediction of the burst time can be done with the static and then the dynamic approach. So, let us see the SJF algorithm first. In the SJF algorithm, it is given to us the arrival times and the burst time of the processes. Here we have a Gantt chart that we have to prepare for all the processes. Let us say the Gantt chart starts at time 0. At time 0, we have only one process available, that is P1. So, let us schedule it at the CPU. This has a burst time of 3. So, it runs up to 3 unit of time. Up to 3 unit of time, P2 has also come, and P2 is the only process which has come up to the 3 time, because P3, P4 and P5 processes will be arriving a bit later. So, P2 process is allocated the CPU and it runs up to 6 unit, it runs for 6 unit of time up to 9. Up to 9, all 3 processes, that is P3, P4 and P5 have arrived. We should select the process which is having the shortest burst time, and that process is P5. So, let us schedule this P5 process on the CPU. It has a burst time of 2. So, it runs up to 11 in the 11 time in the CPU, and then we hand over the process or hand over the CPU to the P3 process, which is the shortest among the P3 and P4. P3 has a burst time of 4. So, it runs up to 15. After this, P4 can take over, which is the last process as per the given system, and it has a burst time of 5. So, it runs up to 20. So, we have scheduled all the processes at the CPU. The Gantt chart is started at 0 and it has finished at 20 as per this numerical. We have to compute the completion time now. I told you in the earlier lectures that for finding out the completion time, we need to traverse this Gantt chart from right to left, and wherever or at whatever position the process appears for the last time is the completion time. So, now P4 process is finishing at 20. So, let us mark the completion time for the P4 process as 20. P3 process finishes at 15. So, let us mark the finishing time of the P3 process as 15. P5 process finishes at 11. So, let us mark the finishing time for the P5 process at 11. Let us mark the finishing time for the P2 process at 9, because 9 is the last time we see the P2 process here. and then P1 finishes at 3 times. So, let us mark the completion time as 3 for the P1 process. Now, let us compute the turnaround time. I told you that the turnaround time is the time that a process spends in the system. After the submission, it will be doing some CPU executions, it will be waiting for something, it may be doing the IO operations as well. So, turnaround time is the total time a process spends in the system. In this particular scenario, the turnaround time for the P1 will be equals to completion time minus the arrival time. So, it will be 3 for P1 process, it will be 7 for P2 process because 9 is the completion time and 2 is the arrival time. 15 minus 4, 11 will be the turnaround time for P3 process. 20 minus 6, 14 will be the turnaround time for P4 process. 11 minus 8, 3 will be the turnaround time for P5 process. Now, the waiting time is the amount of time wasted for a process. It must be doing some CPU executions, the process must be doing some CPU executions, process must be doing some other activities, or it may not be doing any activity and it is waiting for the allocation of the CPU. So, amount of time which is other than the CPU's execution is known as the waiting time. So, we find the waiting time as turnaround time minus burst time. So, in this case, the turnaround time for the P1 process is 3 and the burst time is 3, its waiting time is 0. For the P2 process, it is 7 minus 6, 1. For the P3 process, it is 11 minus 4, 7. And for P4 process, it is 14 minus 5, that is 9. And for P5 process, it is 3 minus 2, 1. So, this is the waiting time. After this, we should compute the response time. The response time is the first time allocation of the CPU to the process. So, this can be found by traversing this Gantt chart from left to right, and here we see that wherever the process appears for the first time is the response time. So, the P1 process appears at 0 time, P2 process appears at 3 time, P5 process appears at 9 time, P3 process appears at 11 time, and P4 appears at 15 time. But this is the relative time. We should find out the response time with respect to the arrival time. So, let us subtract the arrival time of all these processes from their found values of the response time here in this table. So, 0 minus 0 it means 0 is the response time for process number 1, 3 minus 2, 1 is the response time for process number 2. It means that process number 2 has got the CPU 1 unit time later than its submission. Similarly, for P3 process it will be 11 minus 4, 7. For P4 process it will be 15 minus 6, that is 9. For P5 process it will be 9 minus 8, that is 1. So, it is known that, or it was discussed earlier also, that the response time of the shortest job first algorithm is very good with respect to the other algorithms. So, the response time of the shortest job first algorithm is very good, but the round robin scheduling has even better response time. In the SJF scheduling, we have seen that if the longer processes are there and the shorter processes are there, both are arriving at the same time, or we have a chunk of the shorter and the longer processes, then the shorter processes do execute at the CPU and there is a starvation for the longer processes. Fine. Similarly, we have the SRTF algorithm. So, let us look at the SRTF algorithm also once more. So, what happens in the SRTF algorithm? This is the preemptive SJF scheduling algorithm. It is a preemptive SJF scheduling algorithm. Whenever a process or the incoming process is of shorter time than the earlier available ones, or even when a process is running at the system and that has a longer burst time than the arriving process, we will be giving the priority to the shorter process. So, the longer processes will be preempted to give the task of the execution to the shorter process. Fine. Let us see this with an example. We have the 5 processes in the system. Arrival and the burst time of these processes are given. At the 0 time, only one process is available, that is P1. Now, P1 executes for one time only, and after that P2 process arrives. P2 process has a burst time of 3. The remaining burst time of P1 process is 4. The burst time of these two processes means P1 and P2 are compared, and P2 has a shorter burst time. So, let us allocate the CPU to the P2 process, and P2 executes for 1 unit of time, after which the P3 process also arrives. So, now we have 3 processes to compare with, P1, P2 and P3. P1 process has a burst time of 4, P2 has 2 and P3 has 2. So, there are 2 processes which are the shortest ones, P2 and P3. Now, there is a conflict whether we should allocate the CPU to the P2 process or to the P3 process. So, whenever a conflict arises, we take the help of the FCFS scheme. So, since first P2 process has arrived, we will be giving the preference to the P2 process for the execution. So, P2 process continues its execution, and P2 process continues its execution for 1 unit of more time, then the P4 arrives. Now, I have 4 processes now, P4, P3, P2 and P1. Let us compare the burst time of these processes. The 2 of the processes, P2 and P4, have the same burst time. Once again, we will resolve this conflict by the first come first serve scheme. Obviously, the P2 process must have arrived first, then the P4 process, because their process IDs are like P2 has a smaller process ID and P4 has higher process ID. So, let us allocate the CPU to the P2 process once again, and P2 continues its execution till the completion. It has only 1 unit of time left to execution. Now, once the P2 has finished, at 4 time P5 process is also arrived. Now, we have 4 processes in the system, P1, P3, P4 and P5. P4 is having the least burst time. So, let us allocate the CPU to the P4 process. It runs up to 5 unit of time, 5 time in the Gantt chart, and then it finishes. After this, the P3 process is having the least burst time. Since no more processes are coming in the system, we are remaining with the only previously came processes. So, no need of preemption now. The processes will now complete till the completion. So, the P3 process, which is having a burst time of 2, so this process runs till the completion. Then we have the P1 process that also runs till the completion up to 15, and then the P5 process finally, which runs till the completion up to 21. Okay. There is a slight problem. This is 11 and then this is 17. Okay. So, let us find out the results as well in this table. Let us find out the completion time, turnaround time, waiting time and all those things. So, completion time of the P5 process is 17. Looking at the Gantt chart, we should go from right to left to find this out figure, find out this figure. Now, P1 process is finishing at 11, P3 process is finishing at 7, P4 process is finishing at 5 and P2 process is finishing at 4. This is the completion time. Let us find out the turnaround time. We know that the turnaround time is equals to completion time minus arrival time. So, the turnaround time for P1 process will be 11, 3 for this process, 5 for this process, 2 for this process and 13 for this process. Now, after this, let us find out the waiting time. Waiting time is equals to the turnaround time minus the arrival time. So, 11 minus 1, 11 minus 0, 11 is the waiting time for process number 1. Sorry, waiting time is equals to turnaround time minus the burst time. So, this is 7 and for P2 process it will be 3 minus 3 0, for P5 P3 process it will be 5 minus 2 3, for P4 process it will be 2 minus 1 1, for P5 process it will be 13 minus 6, that is 7. Similarly, we can find out the response time. The response time will be equals to the first time the process has got the CPU. So, P1 process has got the CPU at 0 time, P2 process has got the CPU at 1 time, P4 has got at 4 time, P3 has got at 5 time, and P5 has got at 11 time. Let us subtract the arrival times also from this figure, because this is the relative time. So, minus 0, minus 1, minus 2, minus 3 and minus 4. So, this is 0, 0, 3, 1 and 7. If we have to find out the average waiting time and the average turnaround time and the average response time, then you should sum the figures for all the processes and then you should divide it by the number of the processes. For example, if we have to find out the average response time, so this will be 0 plus 0 plus 3 plus 1 plus 7, that is 11 divided by 5. So, this is the average response time for the given system. Now, we have seen that whenever we are doing the SJF or the SRTF scheduling, we need the burst time to be known in advance. This is not the requirement for any other process. This is the only requirement for the SJF and the SRTF algorithm. So, we need to predict the burst time. So, prediction of the burst time can be done in two ways. One of the way is to do it statically and the other way is to do it dynamically. Static means we have certain features associated with the process and those features may be the process type or process priority or the process status. So, we should actually find out the burst time or we should predict the burst time based on their nature. We may also think about the size of the process also while deciding the burst times. In the dynamic approach, we take help of the previous experiences. In this, we have two techniques to find it out. For example, the simple averaging and the exponential averaging. So, let us look at these two techniques in detail. First is the static approach for the prediction of the burst time. Finding out the burst time or predicting the burst time according to the static approach has two approaches. One is you should identify what is the type of the process. Let us say a process is a operating system process. Obviously, the operating system process will be fast ones. They will be having small codes and they will be finishing in a quick succession. So, in case we have the experience in the previous that all the operating system processes are finishing in 5 unit of time or 4 unit of time or 3 unit of time. So, whenever the next process comes and that is the operating system process, then we should actually declare that its burst time is 3 to 5 units. So, this is based on the previous experience. Now, similarly, if we have the user processes, not the operating system process, and we have the foreground process. So, let us predict that its burst time should be 15 to 20 units. You can take any figure in between. Similarly, if you have the background process, then you should declare that the predicted burst time is 10 to 12 units. You can take any figure in between 10 to 12. Similarly, if you have interactive process, the user is interacting with the execution of the process, for example, the games, you can say that the interactive processes do finish in 5 to 8 units. You can select 5, 6, 7 or 8. So, this is the prediction on the basis of the process type. Another one is the depending on the process size. For example, if the old process based on the experience says that on the same system, operating system is doing all these predictions. So, based on the previous experiences on the same system, operating system has found that when the process size was 200 KB, the burst time was 20 units. Now, it is predicting that when in future a process of 201 KB comes, then the predicted burst time will be 20 units. So, it is near to the size of the 200 kb. So, that is why it was selected by the operating system that its burst time, or it was predicted by the operating system that the burst time is 20 units. Fine. Similarly, if the old process was of 100 kilobyte, operating system has found that the old process that was of size 100 kb, it had a burst time of 15 units. Similarly, if the new process is coming of 96 kilobyte, which is very near to the size of 100 kb, then the size of the predicted burst time is 15 units. Take another example. If the old process was of 600 kb and the burst time was 40 units, so the new process of 610 kb which is coming, and we have to predict the burst time for this process, is predicted as a 40 units. So, the burst time prediction of the 610 kb process by the operating system is the 40 units. Now, you consider a situation. There are two types of the processes that we already have discussed. One of the process is the CPU oriented or process oriented, and another one is the IO oriented process. Now, the CPU oriented process will be spending more time on the CPU and less time for the IO operations, and the IO bound process or IO oriented process will be spending more time on the IO operations and less time on the CPU execution. We know that the CPU execution is fast, very fast in fact, and the IO operations are slow. Okay. If we have a 600 kb process, let us say we have a 600 kb process, and the 600 kb process, a 600 kb process which is IO bound, and the 600 kb process which is the CPU bound. Both type of processes cannot be of the same nature, and we never know, or the operating system does not know whether the incoming process is IO bound process or the CPU bound process. So, prediction of the burst time according to the size is perhaps not a good mechanism. We should find out some other mechanisms by which this can be done. So, the other mechanism is through the dynamic approach. Dynamic approach means, let us take the advantage of the previous experiences. We have the actual burst times of the previously executed processes, and we have to find out the burst time of the future process. So, the very first approach for finding out or for prediction of the burst time through the dynamic approach is the simple averaging. Simple averaging means, let us say we have some processes. If we have to find the burst time of a future process, let us average this with the burst times of the previously executed process. For example, if P1 process is of 12 units, P2 process is of 14 units, P3 process is of 22 units, and P4 process is of 7 units, and P5 is of 30 units. In case we have to find out the burst time of P6 process, so that will be equals to 12 plus 14 plus 22 plus 7 plus 30, this divided by the number of process, that is 5. So, this is the method that we have adopted for finding out or predicting the burst time of the future process. So, this is done by the simple averaging. So, if you just compute this value 26 plus 22, 48, 55, 85 by 5. So, 17 is the predicted burst time of process number P6. Now, this prediction is given by the generalized formula, which is tau n plus 1 equals to 1 by n summation I equals to 1 to n T I. Here we are saying that T I is the actual burst time for any process, and tau I is the predicted burst time for any process. So, T I and tau I, the relation between this is tau n plus 1 is equals to 1 by n summation 1 to n T I. Okay. So, this is the simple averaging. Another technique is to do it with the help of the exponential averaging. In the exponential averaging, we have to create a balance between the predicted burst time and the actual burst time. So, we have to take both the factors in the mind while computing the predicted burst times. So, here is a formula: tau n plus 1 means predicted burst time of n plus 1 process number n plus 1, that is equals to alpha T n plus 1 minus alpha tau n. Here T n is the actual burst time of nth process and tau n is the burst time of nth process, predicted burst time of nth process. Fine. Alpha is called the smoothing factor. The smoothing factor means we have to create a balance between the T n and the tau n while calculating the tau n plus 1, means when we are predicting the burst time, then we should create a balance between T n and the tau n. Now, we have to see the experiments before. If the experiments before are showing the good result with the selected value of alpha, let us continue with that. If the value is not near to the actual burst time, or the predicted burst time is not near to the actual burst time, in that case we should increase or decrease alpha, and alpha is usually in the range of 0 and 1. It can take a fractional value. Fine. So, this is the diagram that will actually explain you that how this prediction is behaving. So, this is the tau I and this is the T I. So, initially what is happening that there is a gap between the T I and the tau I, but as the time progresses we find that the predicted and the actual burst time do have a match or they get parallelized. So, with the experiments the actual and the predicted burst times are getting closer. Let us take a numerical to solve this, and then you will be able to understand the exponential averaging even better. So, the value of alpha is 0.5, the smoothing factor is 0.5, tau 1 is 10, the actual burst time of 4 processes T1, T2, T3, P4 are given, and you have to find out the burst time of the 5th process. You have to predict this. So, how can we do so? Let us do it for tau 2. So, how will we be finding the tau 2? So, tau 2 will be equals to alpha T1 plus 1 minus alpha tau 1. So, alpha is 0.5, T1 is 4 plus 1 minus alpha means 1 minus 0.5 into tau 1, that is 10. So, this figure comes out to 2 plus 5. So, this value is 7. So, this is the predicted burst time of process number 2. Similarly, let us find out the predicted burst time of process number 3. So, that will be equals to alpha T1, sorry, alpha T2. So, T2 is 8 plus 1 minus alpha into predicted burst time of second process, that is we already have found the T2, that is 7, tau 2, that is 7. So, this value comes out to 4 plus 3.5 means 7.5. Similarly, we can find out tau 4 as well. So, the value of the tau 4 will be equals to alpha T1 plus 1 minus alpha, sorry, tau T3 and tau 3. So, alpha is 0.5, T3 value is 6 plus 1 minus alpha into tau 3, that is 7.5. Okay. So, this value is 3 plus 3.75. So, this is 6.75. Finally, you can go for computation of tau 5. Tau 5 can be found with the same formula. So, that will be equals to alpha T4 plus 1 minus alpha tau 4. Okay. So, this value can be found as alpha is 0.5, T4 is 7, then 0.5 again, and tau 4 is 6.75. So, this is 3.5 plus 3.875 perhaps. I may be mistaking, you should clear with your computations. So, this will be equals to 7.375. So, I might have done some mistake in the computation of the last step, you should correct it by yourself. So, this is the way we are finding out or we are predicting the burst time in the with the exponential method. So, here is a numerical for you, again you should solve it by yourself. Here we have taken the alpha as 0.6, alpha is representing the smoothing factor, tau 1 is 20, that is the predicted burst time of first process. The actual burst time of the processes are also given, you have to predict tau 6. Now, let me compute tau 2 for you and then rest of the parameters you should compute by yourself. So, tau 2 will be alpha T 1 plus 1 minus alpha tau 1. So, this will be equals to 0.6 into 8 plus 0.4 into 20. So, this figure comes out to 4.8 plus 8. So, this is 12.8. So, 12.8 is the predicted burst time of second process. Similarly, we can find out the predicted burst time of other processes. So, we have seen the merits and the demerits of the SJF and the SRTF algorithms. So, this is the reference for this lecture. Thank you.